Hello and welcome to ABB TechTalks webinar on hydrogen economy, the macro review. My name is Bente Lund Larsen, Marketing and Communications Manager for Electric Solutions in ABB Marine Ports, and I am your host today. First, a couple of practical things. Microphones are muted during the session. The webinar is being recorded and the recording will be made available in a couple of days' time. Our key speakers will present for 20 minutes each, followed by 15 minutes of Q&A. If you would like to ask our speakers a question, please click on the chat icon at the bottom of the screen and type any questions you have in the chat that will open on the right side. You can type your question at any time, and we will address as many of them as we can during the Q&A session. So today's webinar is the second in our series on the topic of hydrogen and fuel cells. You can find the upcoming episode on hydrogen containment and the recording of the previous one on fuel cells for large ocean-going vessels, plus many others on our website. Today we're talking about hydrogen economy, looking at the following topics: the pathway to carbon-free shipping, perspective on hydrogen development and competitiveness, and what it means for marine ports, the near-term priorities from an economic point of view, before we end with the Q&A session. So, it is my honor and great pleasure to present our expert speakers in the order of appearance. Introducing the session from ABB Marine Ports, it's Jostein Bogen, Global Product Manager for Energy Storage and Fuel Cells. From McKinsey Company, we have Bernd Heid, Senior Partner Cologne, who will talk about the global development of hydrogen economy. Next is Greg Pavelek, Research, Innovation and Funding Manager from Hydrogen Europe, who will be digging into what the global movements in the hydrogen economy will mean for the marine and ports industries. Then we have from Ballard Power Systems, it's Nina Hjort, Director Strategy and Market Development, giving insight on fuel cell developments. And me you have already met. So, to introduce today's topic, it is my pleasure to hand the microphone over to Jostein Bogen. Over to you, Jostein.
Thank you, Bente. I'm pleased to see some of the participants today and want to thank you all for joining. A quick recap on what we discussed in the previous episode. On this slide, you see a possible pathway to carbon-free shipping, and you clearly see a transition both in fuel and technology. Over the past years, ABB has been applying shore connection and shore charging combined with batteries. Now we are engaged in a few technology demonstrator projects with the fuel cells in smaller vessels, and at the same time working with Ballard on a multi-megawatt fuel cell system in order to scale up. One of the key challenges today is the availability of clean fuel such as green or blue hydrogen, and that the technology on board are maturing faster than the supply chain of carbon-free fuel. In our discussions with various stakeholders, we often get the question on hydrogen availability and cost and how the supply chain is expected to develop. At the same time, we see many interesting initiatives in ports for scaling up hydrogen production, both on green hydrogen with large-scale electrolysis and on blue hydrogen produced from natural gas combined with carbon capture. We are very pleased to have presenters from McKinsey and Hydrogen Europe with us today to present their view on the hydrogen economy and hydrogen as an energy carrier, either as a fuel on board ships or as the basis to produce other hydrogen-based carbon-neutral fuels. Cost effectiveness and availability of new carriers will play a key role whether they can be used successfully for shipping going forward. McKinsey is here to talk us through the development of hydrogen on a global scale, and Hydrogen Europe will follow up with what these developments will mean for the shipping industry. Thank you, Bente.
Thank you very much, Jostein. it's my great pleasure to hand the word over to Bernd Heid for the perspective on hydrogen development and competitiveness. Over to you, Bernd.
Thank you, Bente, and thank you, Jostein. So what I would love to do is give a short overview on a perspective both on the market and applications of hydrogen, as well as on the question that Jostein already posed on the competitiveness of the cost position of hydrogen applications. So let us start with the overview on the ecosystem of hydrogen applications. And we speak of 7 roles in the ecosystem where hydrogen can play a role to help to decarbonize. So overall, hydrogen is an energy vector, more so than just a fuel for individual applications. You see on the left side of the chart that hydrogen can play a role in the feeding in of renewables into the energy system. Renewables come when sun is shining and wind is blowing. So we have that intermittence associated to renewables. So hydrogen is a carrier to connect renewable power to various applications. The middle portion of this chart depicts the distribution and also the storage of hydrogen. And here comes one key advantage of that molecule to play. Hydrogen is easier to store and also to transport over long distance than it is, for example, the electron alone. So a question that always comes up is, why do we first convert renewable electricity into a molecule to later on reconvert it into other forms of energy? And the simple answer to that is that in some cases you cannot go direct from the renewable energy to the end users where you need that energy. So that's where hydrogen comes in as an energy carrier. On the right side, you see the 4 different applications where we see hydrogen helping to decarbonize individual sectors. One where we also have later on further information from Gregor is on transportation. So that includes road transportation as cars, trucks, or buses. But this includes all other forms of transportation. Think of maritime, think of aviation, be it as hydrogen or be it in the form of synthetic fuel. The second is decarbonization of building heat and power. So one application is, for example, using hydrogen in fuel cells as backup power for data centers. Data centers have a huge demand on power increase, so the backup power is easier to store in the form of hydrogen than it would be in the form of a battery. We have industrial applications, and these are typically sectors that are called hard to abate sectors. So think of all sectors that use high-grade heat, cement, aluminum, or steel production. And hydrogen is a substitution for the production of steel. Think of the reduction of iron ore to raw iron that can use hydrogen instead of metallurgic coal in the met coal process. And last but not least, that is where we use hydrogen already today. So the molecule is not a new invention, but it's widely used in chemical and petrochemical processes, such as refineries or as a precursor for ammonia production. So the problem here is that this is today largely gray hydrogen. And when we speak of gray, it means hydrogen produced from a process that is called steam methane reforming, that is CO2 emitting. So replacing that with either green from renewables or blue using carbon capture and storage are 2 forms to decarbonize hydrogen production process, and thus also reducing the emissions of this process industry. So if we look at the overview on the electrolyzer capacity, what you see on this chart is the global electrolyzer capacity. And you see that as of today, we are at a level of roughly 90 megawatts globally of installed capacity. And this goes up to more than 11 gigawatts until 2025. So that's a very near-term future. One interesting fact about this chart is that you see almost like Marx. We draw this chart the first time in June last year, and the message was that the electrolyzer capacity increases from 90 megawatts to 1.8 gigawatts. And as we speak, this data gets faster outdated than we can add to it. In March it was 8.6, and now we are at 11. Important here is this is not just a projection by a McKinsey team. This is real projects, and I could give you an Excel list behind with name of the developer, which country, what's the size that's being installed. So they are projects in commissioning. We still believe that this is underestimating the true deployment that we will see. So, for example, Europe announced 40 gigawatts of electrolyzer capacity until the end of the decade, and potentially even an increase to 80. The reason why I say so, it is important to have electrolyzer deployment in order to reduce the capex of the electrolyzer, which is supposed to decline over the next years while being deployed. And I will show you in a bit the cost structure. So on this chart, you see the various government programs from the European Green Deal. You see that countries like Korea have plans existing, but very recently, for example, Germany has announced 9 billion euros that go into the hydrogen ecosystem. France almost simultaneously announced 7 billion, and you have large-scale deployments in planning and production already in the Netherlands. So the important message here is a lot of that happens post-COVID. So that was a big question. Will COVID put a halt to all of that deployment? And what we can see from all regulatory backgrounds at this moment is that it's rather accelerating than slowing down. So when we look at one of the most important ingredients for this energy transition and the application, be it maritime or others, is the cost of hydrogen. What you see on this chart is today's cost of hydrogen derived for green hydrogen, that is from renewable power, somewhere between $3 and $6 per kilogram. You also see on this chart gray, which is hydrogen from steam methane reforming. Blue hydrogen is low carbon hydrogen that uses gray and the carbon capture or storage process. So the main point in our research is that hydrogen will come down in the cost structure over the course of the next decade to somewhere a level of $2 to $3 per kilogram. And this is exciting news because that will enable that hydrogen can be cost competitive to other applications in the not so distant future. This data here is again not just a modeling, but in the end this data was obtained from an analysis that we conducted jointly with the Hydrogen Council members. So in essence, this stems from a clean team effort where we collected 25,000 different data points across all applications. So therefore, this is something that is industry consensus and can also be achieved. If you look further, a second important step is the electrolyzer itself. So the currently used technology today, that's mostly alkaline electrolyzers. That's an existing technology. And here you see that over the course of the next decade, you see the hydrogen costs from electrolyzers coming down from somewhere $700 euro per kilowatt of installed capacity to somewhere around 400. A second technology, that's PEM. For PEM, the picture is very similar. Although this is a nascent technology today, where we have costs that exceed 800 euros per kilogram, you see in our assessment that we will be even at a level that is at par or even below alkali in the distant future. A third technology that is solid oxide. Solid oxide operates with high temperature at 800 Celsius. Today it's a very tiny technology that's only deployed in first prototypes. However, depending on which application you have, be it, for example, synthetic fuel, where you have excess heat that can also help to increase efficiency, you will reach levels that are competitive also to alkaline or PEM at higher efficiency grades if that additional heat or process energy is existing. So all of that taken together gives us a market increase in various applications, which you see from power generation, transportation. That is also where we find maritime applications and the other sectors that I mentioned. Overall, we see an 18% of the final energy demand that can be powered by hydrogen until 2050. So while you argue that 2050 is in the very long future, we were the first who came out with such a projection. However, in the meanwhile, we had other sources, be it IEA, be it IRENA, be it Bloomberg, that are in very similar ballparks, plus minus a few percent on a very similar message. So in the more near-term future, there are two framings how you could think about it. So from 2020 to 2030, there's one view to look at it. That's the increase from 2,700 terawatt hours to 3,900. For your reference, the 2.7, that is equivalent to 80 million tons each year. But the second view how to look at it, and that explains also some of the momentum that we currently see, is that you have today's clean or decarbonized hydrogen production is zero. All of what you find here is more or less gray hydrogen from CO2 emitting processes. So a second framing is that we will see an increase from zero to the delta of what comes new on top, because all of these new applications make only sense if you use decarbonized hydrogen, and at the same time we see a replacement of gray hydrogen in the feedstock applications to green. So the second framing is that we increase from somewhere 0 to 2,000 terawatt hours of green hydrogen, and that is also why you see that tremendous momentum right now being present. So let me shift gears and look at the cost competitive of the various applications. When we did that analysis with the members of the Hydrogen Council, we looked at two dimensions. The one is hydrogen more or less competitive than the next conventional technology. That is, for example, diesel or heavy oil compared to hydrogen. And we did a second analysis, that is hydrogen the cheapest low carbon emitting solution, or is it better to power an application with, for example, batteries or direct electricity? So therefore, this was not only an analysis on hydrogen itself, but it was hydrogen vis-a-vis the CO2 emitting and decarbonized alternatives. On this chart here, you will see the different applications, and let me talk you through some of them. So you see on the upper right corner, you will find 9 applications where hydrogen is the best alternative vis-à-vis conventional and the best alternative vis-à-vis zero emission. So that's why you see, for example, right now, a lot of momentum in heavy-duty trucking, because it's, from a TCO perspective, even more cost-effective to power a truck with hydrogen than to go on diesel. And you see also other applications in here, ranging from buses to trucks, forklifts, regional trains. There is another set of applications that are in the upper left corner. And here the logic is, this is the best alternative to power zero emission applications. However, it comes at a cost. If it were cost neutral, it would be on the middle line. And as it's to the left of the middle line, vertical line, it means it comes at a cost to decarbonize. So here you see also additional applications. And if you draw vertical lines roughly at the refinery, that's 50 euro per ton of CO2, that's 100. So the further you go to the right, the more expensive, or the higher is the cost to decarbonize. But nevertheless, you have applications where there is a pathway to decarbonize that is still the best to be done with hydrogen. And that was one key learning, that we say it's better to use hydrogen in certain applications than the next best alternative. So if we look at the production of hydrogen, we see the world being divided in two different lenses. On the left side, you see dark green areas where hydrogen can be produced cost effectively at $2 per kilogram if you find dark green areas, such as Australia, India, Middle East, North Africa, parts of Iberia, and the west of the US. Plus, you hardly see it, but Chile has ideal positions to produce renewable energy and thus also green hydrogen. But we will not only see green hydrogen, we will also see blue hydrogen. And this depends on two factors. You need to have cost-effective natural gas existing, such as Russia, US, Middle East, Southeast Asia, and there needs to be carbon capture capacity available. While this is politically not wanted in parts of Europe, you see that in Norway or the UK that this is feasible, and also we will see carbon capture projects being certainly deployed in the US, in Russia and Middle East. So therefore, in our view, we will see both technologies in the future, and it's just a matter of what will be the local deployment and what will be the share of it, but we will see the coexistence of these technologies. So this brings us also to one point. In order to make that hydrogen on a global scale available, if you do not want to produce it locally, you need to transport it over long distance. And we have 4 different routes how we could do it. Of course, we could ship it as liquid hydrogen in vessels. Right now, there is predominantly Kawasaki Heavy as one of the first pioneers in this technologies to transport hydrogen in a liquid form. Because that is not yet scaled up and commercialized, we also have the next best alternative is to ship hydrogen in the form of ammonia, because that's a standardized process. Ammonia can be transported across the world. You have challenges if you want to reconvert it back to hydrogen, but there are a lot of applications. Think of fertilizer production where you need hydrogen. 2 more technologies that I would love to shortly highlight, that's shipping it in a organic chemical compound. So that's LOHC. It's a niche technology and nascent. So it still needs probably more than 10 years to be fully deployed. And you could also use an existing process like LNG shipping. However, then as you also ship a fuel that is CO2 emitting. If you produce hydrogen, you need to recycle the hydrogen back, also in a liquid form, and the ratio is roughly 10 vessels going one direction and one coming back. And let me finish with one message on the last chart, and that is where we have shown a couple of different projects that are currently deployed globally. And you see on the one hand, green hydrogen replacing blue for all sorts of applications, be it in refineries, be it in fertilizer production. You have applications where you use it in industrial settings for steel or others. You have it in transport, like heavy duty transport for trucking. And you also see projects that produce hydrogen for an international market, so that will be the export market. While we believe that most of the hydrogen today will be produced regionally, as we do not have that international market available as of now, we also believe that there will be a merchant market, probably in the early 30s, where you have hydrogen available in ports and international infrastructure, so that we also see a global market for that being deployed. And as a last note on this chart is you also see that this is an ecosystem game. There's not a single project, and we could continue a list to 100 projects globally. There's not a single project that is done with one company alone. Almost all of the projects are done in conjunction with players along the value chain, as this is not a single value chain step, but rather projects that span across a broader ecosystem. I thank you very much and would like to hand over the presentation to Gregor.
Thank you very much, Bernd. Let's have a deeper look into what this all means for the marine and ports industry. I'm very pleased to hand over the microphone to Greg Pawelek.
Good afternoon. Thank you, Bernd, for inviting me, and thank you, Bernd, for this great introduction to the topic. What I would focus on today is more on to have a closer look at how hydrogen can play a role in the maritime sector, let's say. And in order to do that, I'd like to first start with the hydrogen as a fuel, which is one of the applications, but it is by far not the only one application that hydrogen can have in the maritime sector. Starting with this, what you can see here on the slide is clearly we're not starting from scratch. There have already been some projects that are being developed and are being developed. And you can see that the scale of ambition and the scale of the project is growing every year. What you can see on this slide, particularly, are projects funded by the Fuel Cell and Hydrogen Joint Undertaking. But even though the projects are moving and the scale is growing and the sector is looking at hydrogen as an option, those are all still just R&D projects, pilot projects, not really any widespread implementation. And in order to do that, to move out of this R&D scale, there are a number of challenges that we need to overcome first. Of course, one of that is that there is a lack of bunkering infrastructure. Still some R&D is needed for the large scale fuel cells, for example. But one of the barriers I would like to focus on today is the fact that there is still no consensus about what the fuel of the future will be in the maritime sector. As you know, there are many options. You can talk about biofuels, electricity as a way of propelling ships. There is hydrogen, liquid, compressed, methanol, ammonia, and all those many options. And you can clearly understand why before we move forward, we need to at least limit the options. You cannot expect the ship owners, we know that the ships are expected to have a 30-year lifetime or even more, would invest millions of dollars into options that they are not confident will be able to use that ship in 10 years' time, for example. You can also not expect the ports to be able to provide bunkering infrastructure for 10 different fuels. So it's clear that we need to at least start limiting these options. number of them. And we have at least tried to tackle this problem by developing a kind of technology comparison tool where we look at costs of those different options. Well, I don't have time to go into detail into all the aspects of the tool and all the aspects of the analysis. I would like to just point out the fact that other than just looking at production costs of different fuels, we have also tried to look at the, let's say, monetary or financial impact that the ship owners would face from the fact that both hydrogen and hydrogen-made fuels are usually less energy dense than the HFO, for example. And this has huge consequences for the ship owners as wanting to carry the same amount of fuel or to be able to cover the same distance. This would, of course, limit the cargo carrying capacity of the ships. And this would, of course, negatively impact the revenues that they will be able to generate from the ships. So looking at all that, well, before I go to that, I would like to first have a look at the sheer hydrogen or alternative fuels production costs. On this graph, you can see what it would cost in 2030 to produce those different fuels, taking into account just the production cost and also the, let's say, transformation cost. So in the case of compressed hydrogen, this is just compression. But in the case of liquid or methanol, for example, you need to synthesize the hydrogen with, for example, CO2 that you capture from the air, for example, which makes the whole process more capital intensive and more energy intensive. And having said that, it becomes quite obvious that the pure hydrogen options, let's say, so compressed hydrogen, liquid hydrogen, are always cheaper than the synthetic fuels when you look at just the production costs of the fuels, which is a direct consequence of the fact that it just takes less energy and less, it's less capital intensive to be able to produce those fuels. And then on the second part, when you look at the synthetic fuels, there ammonia is always also the cheapest option. And this is also a direct consequence of two things. One, it does not require the carbon molecule. So you are not faced with the problem of having to source CO2 from somewhere, either from direct air capture or from some kind of point capture from industry. You don't have to synthesize it. And the other fact is that synthesis of hydrogen and nitrogen is exothermic, which is, I mean, doesn't require any energy input, it just creates energy. So when you take those two facts into account, as I mentioned, it is indisputable fact, whatever assumptions you take about the renewable energy costs in the future, ammonia will always be the cheapest synthetic fuel. But then looking at the impact in terms of the storage side of the storage, here the situation is an exact opposite of the production cost of the fuel. Here is that the fuels that are the cheapest take the most volume in terms of tanks, in terms of potentially maybe reforming also on board, than the fuels that are more expensive to produce, but the energy density properties are much better. And in extreme cases, you can end up with having to increase the tank size and the whole fuel system, let's say, volume in a ship by a factor of 10, for example, compared to MGO in this case. And this, of course, might have huge consequences for the ship owners. And this is shown on these two graphs here. So both of those have exactly the same scale, so exactly the same parameters. And you can see while in both of those cases, the relative, let's say, comparison or score of different options is the same. So the compressed hydrogen is always the most expensive one. So that is the case in both of those ship types. But if you look at the deep sea shipping applications and compare it to short sea shipping applications, you can clearly see that even though in those short sea shipping applications the compressed hydrogen is still the most expensive one in absolute terms, monetary terms, while the cost is maybe not negligible, it is clearly becoming more manageable. And then if you combine this takeaway with the previous conclusion that the pure hydrogen options are the cheapest one, but take the most space and it costs more, you can clearly see that there will not be in the maritime sector a winner takes all, or a solution that fits all ship types. This is exactly the conclusion that we have arrived at in our comparison tool, and this is what you can see on this graph. So here you can see that the very short sea shipping applications, where you don't need to refuel the ship more than, let's say, 100 or every 200 nautical miles, it's possible to for compressed hydrogen to find its place on the market, because, as I mentioned, it's just the cheapest fuel, and in such short distances, the impact from the lost cargo space is just negligible. Then there is a large part of the market where the liquid hydrogen looks like the most cost-competitive option. But for the very deep sea shipping applications, it's still very hard to use the pure hydrogen options. And there, probably the fuels to look at are the synthetic fuels. As I mentioned before, the liquid ammonia or e-ammonia or green ammonia, whatever you would like to call it, always comes out to top and is the cheapest option out of all the synthetic fuels. So while this is still not a perfect picture, because we don't have a single solution that works for all, I think it's still quite a potent result that at least we might start to talk about limiting the number of options that are being developed and looked at. But the other aspect I'd like to focus on is that hydrogen has its place in the port ecosystem not only as a fuel for ships. It's a bit different than, for example, what happened in LNG, where the question was always only about delivering the fuel to the ship. So here you can talk about building a broader ecosystem around hydrogen in the port area, because not only can hydrogen be used as a fuel, it can also be used to, for example, decarbonize the port operations. So the equipment that is used for the reach stackers and trucks and all the other vehicles that are used to handle materials. It can also be used to decarbonize industry that is in the port area, which makes the question of hydrogen more like a web than just building a simple link between the shore side and the ship side. And here you can see an example of one of the projects that looks into using hydrogen to decarbonize the port operations. This is an example of the Port of Valencia. Okay, the scale of that is not big. It's just a demo project. It's also one that's funded by the FCG, which I mentioned earlier. But you can clearly see that this approach is possible. And also you can also think about maybe using hydrogen in the future as a way of providing the onshore power supply in certain ports. As you might know, there are large problems that some ports face with being able to provide that onshore power supply. And that's because first, it takes a lot of money, a lot of investment in order to be able to upgrade all the quays in a port to be able to provide the necessary power to provide the onshore power supply. And then, since this investment and then this equipment is not used the whole year over, especially for the likes of cruise ships, for example, it makes it very hard to get any positive return on that kind of investment. Then there is also another question that some ports just might not have the necessary grid connection that is needed to be able to provide that power to those large ships. And then kind of this mobile hydrogen power supply might be a way out of that problem. But another issue would like to focus is that the use of hydrogen to decarbonize the reach stackers is obviously a good thing to think of, but the scale is not also there to be now. But when you look at the hydrogen industry as it is today and look at where hydrogen is consumed and produced today, you might see and notice that a large part of it already takes place in either in directly in ports or in the port area or near ports. Just looking at, for example, Antwerp and the four Dutch ports, the four main Dutch ports, the hydrogen economy that is already there, the hydrogen consumption for industry like ammonia production, so the fertilizer industry, like oil refining, methanol production, just those 5 ports currently consume around 1/5 of the whole hydrogen consumption in the entire Europe. And then on top of that, you can see that, as I mentioned, hydrogen is potentially one of the fuels for shipping. You can see that you can use hydrogen to decarbonize the port areas. There are also other industries that can be potentially decarbonized using hydrogen, as Bernard has mentioned, the steel industry, for example. There are large steel mills also in Europe, in Hamburg, also in the Dutch ports. And then you can also see that there are synergies to be exploited with the offshore industry that also is closely connected to the ports. And you combine all that together, you can clearly see that the ports are clearly shaping up to be really a key players in developing the hydrogen economy going forward. They can really act as this kind of hydrogen hubs. As I previously mentioned, the case of developing hydrogen project, and this is also something that Bernd mentioned. You need many players to work together, and this is all more than just building a link between two. You need a whole web of players and connections. And as you know, every web needs a spider, and here the ports might not be the most pleasant analogy, but still, here the ports can really play a huge role to making this happen, to building those links and creating this local ecosystem. And of course, if you look at what's happening in the port areas and the hydrogen projects, and some of them Bernd has also mentioned already, you can see that ports are clearly seeing this. And there are already a number of hydrogen projects being developed by ports. Here you can see a couple of examples. The Port of Antwerp, Port of Rotterdam, both are members of Hydrogen Europe. They are developing large-scale hydrogen projects. But there are also a number of either smaller ports or smaller projects in the same area. You see that there is the Hydrogen Valley being developed in the northern Netherlands, which is also built around a port area. Includes a number of different applications for transport, for shipping, grid balancing, also for industry. So those are not isolated projects, but some of the largest projects that are currently developed are all being based around in ports or around ports. And here you can see a couple of examples. One is what I mentioned already, Port of Rotterdam. And you have clean hydrogen production, both about green renewable hydrogen and blue hydrogen, so low carbon hydrogen from natural gas with CCS, which is then going to be used directly in the port area by BP and Shell refineries. And here you can see that, I mean, one of the reasons why the hydrogen economy is still early in its development are the costs. But there are two ways of bringing the costs down. One is the continuous improvement in the capital costs needed, as Bernd said, and this is still going on and will fall down. But currently, a lot of that might just be not from any technological breakthrough, but just from upscaling of the production process. And the ports give a unique opportunity that you can build, start thinking about really big projects without building expensive hydrogen transport infrastructure, because it's just all in the same place. And here you can see one example of exactly that. And another example is the port, is the Hydrogen Valley, which I mentioned in the northern Netherlands. Here you can see that the ambition is to start with 3 to 4 gigawatts, which can then be progressively increased into up to 10 gigawatts of green hydrogen production around 2040. And you can see that out of that volume of hydrogen production, so between 300,000 to 800,000 tons per year, most of it will go to the industry that is located inside the port, so to produce methanol and to produce ammonia. Of course, there are also some mobility applications like buses, passenger cars and trains. There's also some volume for grid balancing. But without the industry, you would never be able to build this kind of large-scale projects locally without building an extensive refueling infrastructure. And this is really a prerequisite to build to think about building a positive case, this high scale. And I cannot stress this enough that here ports can really play a huge role. So just to finish up with my presentation, I would like to make this kind of a couple of central observations. One is that what I mentioned about when I talked about different fuel options is that independent from the fact which fuel will turn out to be the winner, will turn out to be the most commonly used options, all of those fuels are made from hydrogen. So either it's ammonia, diesel, pure hydrogen, whatever. All of those fuels will require hydrogen to be produced. And then when you look at all the regulations and push for decarbonization of the shipping, you can clearly see that all those initiatives will create a huge demand for hydrogen in the future. And if that is a consequence that can be accepted and is understood, then you can also clearly see the way to the second consequence, which is the fact that the port area is really shaping us as the key players and key hydrogen hubs that will develop and are needed to develop the hydrogen economy. And with that, I would like to end and give the floor back to Bente. Thank you.
Thank you very much, Greg. I would like to remind you in the audience that there is space for more questions, so please feel free to type your question in the chat, and we'll get to that very shortly. To warm up for the Q&A, we would like to do a little poll. So there should now be a poll in your poll panel on the right side. If you cannot see it, go to your bottom panel with the 3 dots on it and select poll, and then you will be able to find the poll on your right side and answer it. While we're waiting for the poll, if you have questions, I'm very happy to receive them in the chat. And now you should be able to see the results in the poll panel on the right. It looks like compressed H2 is what's most frequently being looked into, or primarily being looked into by our audience. Anyone want to comment on that result? Maybe Greg?
Yes, very interesting results. I would expect more votes to the liquid and ammonia, for example, but it's quite interesting and results. I mean, the 3 fuels that I mentioned are still the 3 on top I see, just that I would expect a bit different relative score of those, but it's quite interesting to see compressed hydrogen being so highly looked at. Yeah. Quite interesting, I would say.
Thank you.
It's also interesting to see that the methanol and LNG are way down the pecking order, let's say.
Thank you for that. Bernd, maybe you want to comment on it as well?
Certainly. So I would also have expected a slightly different focus on ammonia for shipping, and also in the longer term liquid hydrogen, for the simple reason that if you want to carry real large energy sources, then liquid hydrogen will be the denser energy as compared to compressed. The reason why I think compressed is higher than liquid now is because we do not have a liquid infrastructure widely existing at this moment. So therefore what you have in most places is compressed. So that's at least why I think this initially counterintuitive result makes absolute sense.
Thank you. Jostein or Nina, do you have anything to add?
Yeah, I think it's very well answered already by Bernd and Greg, but maybe to add to that, what we also see in our discussions is that, liquid is obviously a less mature technology, and as Bernd also pointed out, it's the infrastructure for liquid hydrogen is lacking as of now. So of course, it also depends very much on the vessel type, vessel operation, and possible bunker frequency on the selection between liquid and compressed as such. Also note that it's interesting, I'm not sure if you have seen the Shell report that came out last week or early this week, where they are also betting on liquid hydrogen as one of the main options going forward in Shell's view. So it's indeed interesting to see.
If I should comment, I can only echo what's already been said, and just in point to that the availability of liquid hydrogen is not really strong yet. And from a fuel cell perspective, from a pan fuel cell perspective, they don't really care whether it's liquid hydrogen or compressed hydrogen. So I think this is the comments I would have from my side.
Thank you. All right, so let's dig into the questions. The first question is to Greg on the hydrogen production facilities in port. When will we see the first large-scale facilities for production in operation, do you think?
Well, the large-scale production facilities in ports are already there. The thing is they are currently used to produce hydrogen that's needed for the refining industry in ports, to the methanol industry and ammonia industries in ports. So the question is when we will see large-scale hydrogen production from renewable sources. That will of course happen soon because those projects are already in the pipeline. We ourselves have already gathered a database of projects that have a combined power or capacity of 20 gigawatts by 2040 in Europe. So that's already quite a lot. We might know that the EU strategy talks about producing 1 million tons of renewable hydrogen by 2024. So that's quite in the near-term future. But the question is, of course, when we'll be able to produce it at a price that will be cost competitive. And here the answer is a bit more difficult. Because the renewable energy costs are falling down, and I don't think this trend will stop anytime soon. And the scale of the projects is increasing, and when we combine those two together, we clearly see that this perspective of being able to match fossil fuel hydrogen can clearly happen sometime between now and 2030. It's debatable whether it will be 2032, 2035, or 2028. But I'm quite confident that it will happen, and it will happen rather sooner than later.
Thank you very much. Anyone else want to comment on that? That seems to be fine. We'll take the next question. Do you see the hype behind the hydrogen companies such as Nikola solely as a good thing, or are there pitfalls in it? For instance, if the industry is not able to deliver results fast enough and the hype or the funding goes away?
Maybe I start with that question. I think this is a very individual discussion and conversation. So if you look at the momentum, what is behind that sector, this is far more than an individual company. So if you look at the full value chain, there are companies like Shell, BP, Aramco, Linde, Air Liquide, large car makers, Toyota, Hyundai, and the like. So therefore, that's far more than just an individual company. I think what is partly behind that individual story is that, of course, the market of the pure play hydrogen players, that's a very small one. That's probably 2 handfuls of companies that that are solely working on hydrogen. Think of Ballard, Nel, Nikola belongs to it, and a few others. So therefore, the attention is very much on it. Whether Nikola will continue on these plans or not, I think will not change the wider ecosystem that you see. The Hydrogen Council alone is 90 plus companies, all leaders in their field. Even if one drops out or doesn't pursue that strategy, there's still sufficient momentum. And I think next to that private sector momentum, you should also see that there is an undisturbed public momentum of governments behind it. So European Green Deal, all of these national plans, this is nothing that you can revert in a few weeks or months. So therefore, the combination of private sector, public sector, and the investor scene that is largely looking for investment opportunities in this field. These are, I think, arguments over and on top of the decarbonization efforts that we see that will make this continue regardless of whether you see a bit of a turmoil tactically here and there.
Thank you, Bernd. Anyone else want to comment on that? That seems to be fine. Okay, thank you. Here's a question for Nina as well. What is Ballard doing to drive down the total cost of ownership of technology from the fuel cell supplier perspective?
Yeah, so thank you, Bente. Yeah, of course, the fuel cell part is also an important element of the total cost of ownership. And what we have seen over the years is a drop in from a fuel cell vehicle side of 65% over the past 10 years. And obviously, a lot of this has to do with the innovations in the technology and the product improvements. And going forward, studies like the McKinsey study published by the Hydrogen Council estimates a drop between 70 to 80% cost in the fuel cell technology over the next decade. And what Ballard is really doing here is focusing on 4 key elements. The first one is really looking at how to build strategic industrial partnerships to accelerate the industrialization of the fuel cell manufacturing. And this is done, for example, by the partnership we've made with Weichai China, one of the largest industrial companies in the motive industry. And the second thing is really leveraging on the supply chain development to access diverse suppliers and mature the whole supply chain behind the fuel cells, and to develop low-cost, reliable components for the fuel cell powertrain. And obviously also Ballard has internal projects going on to reduce our fuel cell stack costs. We are continuing to improve our processes and our membrane electrode assembly lines and in general the stack designs. And we are working on key improvements in these areas. Lower cost carbon instead of metal is one of our strategies. Automating our production lines is a second one. And then implementing process design and throughput scale-up to improve the production yield and support future growth. And then the fourth and the final key element that we are looking into is really refining our recycling and refurbishment processes. And the ability for fuel cells to recycle the catalyst and reuse bipolar plates and refurbish the fuel cells are a real advantage, not only for Ballard, but also for our customers. So doing so, we really lower the total life cycle cost of our products and reduce the environmental impact as well, which is a key important element too.
Thank you very much, Nina. We are over our time, so let's just fit one more question in before we round off. Here's one. Compared to MGO, please comment on the equivalent need for storage space of hydrogen, liquid hydrogen, and ammonia. Jostein, maybe you want to answer that.
Yeah, I can give it a try, and as also pointed out by Greg in his presentation, we see that storage of the fuel itself for hydrogen is obviously taking more space. But what we also see in the concept design that we are running is that by taking out the combustion engines, you will also be able to free up much space. So I think it's important to kind of rethink the whole design of the vessel around the fuel type and energy conversion that needs to be applied, and then look at the, let's say, total space optimization. But to be more concretely on the, let's say, storage capacity on MGO compared to compressed, maybe Greg want to comment that from his study.
Yes, I can add to that indeed the ship design makes a lot of difference. So we have just looked at the simple comparison of the energy densities and the tank systems that are needed. But for example, if you have a multi-deck cruise ship and you can remove all the exhaust treatment systems, that can save up a lot of space. That can go a long way of kind of elevating the energy density properties of hydrogen alone. Then of course you have energy improvement measures that you can take with the hull coating improvements, with wind assistance. All that combined can make the problem of energy density of hydrogen and the fact that it will indeed take a lot more space than the MGO, but those measures combined can make the problem manageable. And I clearly don't. It is clearly an issue that needs to be dealt with, but I don't see it as a showstopper.
Thank you very much. All right, that concludes today's ABB Tech Talk session. Thank you, Bernd. Thank you, Greg, Nina, and Jostein for sharing your insights on hydrogen economy and the effects on the marine and ports industries going forward. Thank you also to everyone in our audience for participating in the webinar and the poll and for your excellent questions. For any unanswered questions, we'll get back to you as well. Please join us again on October 28th for the next episode on the topic of hydrogen, this time on fueling the change, about liquid and compressed hydrogen containment. And the panelists then will be from Chart Industries, Hexagon Purus, Hyon, and Ballard Power Systems. See you then. Thank you.